Welcome to another deep dive. Today, we're going to be tackling machine learning head-on.
Yeah.
We've got a whole bunch of university-level course materials
Oh, wow.
to dig through. And whether you're trying to, get ready for some big meeting or just, you love learning new things, I think this is going to be a really fun one for us.
Yeah.
So I think it would be good to kind of lay out for the listeners what exactly we're looking at here.
Okay.
So we've got Quizlist.pdf, boosting.pdf, consistency.pdf, deep.pdf, intro.pdf, kernels.pdf, nn.pdf, linear.pdf, nnrisk.pdf, online.pdf, statrisk.pdf, surrogate.pdf, svm.pdf.
Well, that's a mouthful.
And treepred.pdf.
Okay.
So quite a bit of stuff to dig through.
Yeah. Lots of material.
So I guess let's just get started. Intro.pdf starts off by talking about supervised learning.
Okay. Yeah.
So I guess maybe you could explain that a little bit for our listeners.
Yeah. So supervised learning is basically like, imagine you're teaching a kid like different animals. You show them pictures and you say dog, cat, bird.
Right.
It's basically that. But for machines, so we give them labeled data examples with known inputs and outputs.
Okay.
And they learn to map those inputs to those outputs.
So it's all about learning from examples.
Yeah, exactly.
So intro.pdf even mentions filtering spam emails as an example of this.
Yeah, it's a great one.
I'm guessing it's like it analyzes a ton of emails that are labeled spam or not spam.
Exactly. Yeah, the algorithm would look for patterns in the data.
Okay.
Like certain words or phrases that are commonly found in spam messages.
And then over time, it gets better and better at it.
Exactly. The more data it sees, the better it gets.
Okay, so how do we know how well it's actually doing, though?
That's where loss functions come in.
Loss function?
Yeah, think of it as like a scoring system.
Okay.
It measures the difference between the algorithm's predicted output and the actual true output.
So, if it predicts that an email is spam and it is spam, then the loss function would be very low.
Exactly. Yeah, ideally it would be 0 in that case.
Okay.
Which would indicate a perfect prediction.
But it gets interesting because there are different types of loss functions, right?
Yeah, there's a lot of them.
Intro.pdf mentions logarithmic loss, which has this really interesting property of penalizing overconfidence.
Yeah, that's a cool one.
So, if it's really sure but it's wrong, then it gets hit harder.
Precisely. Yeah. It encourages the algorithm to be more cautious and calibrate its predictions better.
Wow, that's really clever.
Which can lead to more reliable results in the long run.
Okay, now, what about noisy labels?
Yeah.
Intro.pdf mentions those as well.
So noisy labels are basically errors in the data. Like labels that are incorrect or inconsistent.
So, I guess that would introduce uncertainty.
Yeah, it's like trying to teach a kid to recognize animals. But some of the pictures are mislabeled.
Right, it would be hard to learn.
Yeah, it would create a lot of confusion.
So noisy labels, I guess, are just a big problem.
Yeah, it's a big challenge for sure.
Okay, let's move on to a specific algorithm.
Okay.
K nearest neighbors, or KNN from knn.pdf.
Oh, yeah, KNN.
It seems like it's all about, finding the nearest neighbors.
Yeah, it's a cool algorithm.
To a new data point and then, letting them vote on its classification.
It's kind of like a popularity contest, right?
Yeah.
So imagine plotting all your data points on a graph.
Okay.
And to classify a new point, you just look at its K closest neighbors and let them vote on its label.
So if most of them are spam, then the new point is probably also spam.
Exactly. Yeah, it's very intuitive. KNN.pdf actually provides a visual representation of this using what are called Voronoi diagrams.
Okay.
So imagine dividing the data space into regions.
Okay.
Each region represents the territory dominated by a specific data point.
It's like a map or something.
Yeah, exactly like a map.
Okay.
Where each region is controlled by a different label.
So knn.pdf also mentions that choosing the right K value is important.
Oh, yeah, that's key.
The number of neighbors to consider.
Yeah.
Why is that so important?
Well, if K is too small, the algorithm can be really sensitive to the quirks of the data. It can overfit the data, meaning it does well on the training set,
Okay.
but poorly on new unseen data.
So it's basically memorizing the training data.
Yeah, it's like memorizing instead of generalizing.
But then on the other hand, if K is too large, then
Then it might miss important local patterns
okay.
and underfit the data.
So it's like you got to find that sweet spot.
Yeah, finding the balance is key.
Okay, knn.pdf uses the breast cancer Wisconsin dataset as an example.
Oh, yeah, that's a good one.
To show this trade-off.
It illustrates how different K values can lead to very different accuracies.
Now let's switch gears a little bit and talk about linear predictors from linear.pdf.
Okay, yeah.
I gotta admit, like, hyperplanes always kind of make my head spin a little.
Yeah, they can be a bit tricky.
So, I guess like a hyperplane is just a way to divide data in a multidimensional space?
Yeah, basically, so in 2 dimensions, it's just a line.
Okay.
3 dimensions, it's a plane.
But then like higher dimensions, it just gets hard to visualize.
Yeah, it gets abstract.
So, how does linear.pdf connect these hyperplanes to like classifying data points?
So imagine you're drawing a line on a graph to separate 2 groups of points.
Okay.
A linear predictor does something similar, but in a higher dimensional space.
Okay.
It tries to find a hyperplane that separates the data points belonging to different classes.
So if the points can be neatly separated by a hyperplane, then a linear predictor should be able to classify them pretty well.
Exactly.
Linear.pdf mentions that minimizing the 0-1 loss is a way to find like the optimal hyperplane.
Yeah, the 0-1 loss is just a way to count MIF classifications.
Okay.
So if a data point is correctly classified, the loss is 0. If it's misclassified, the loss is 1.
So we basically just want to minimize the number of ones.
Exactly. Yeah, you want to minimize the total number of errors.
But finding that optimal hyperplane, though, can be hard.
Yeah, computationally, it's a tough problem.
That's where the perceptron algorithm comes in.
Ah, the perceptron.
Linear.pdf highlights it as like the simple but effective way to find those separating hyperplanes.
Yeah, it's a classic algorithm.
So how does it actually work?
Imagine like a tireless worker that starts with a random hyperplane.
Okay.
And keeps adjusting it step by step.
Okay.
Based on the misclassified data points it encounters.
So like it's just nudging it in the right direction.
Exactly. Nudging it until it classifies all the data correctly.
And linear.pdf even mentions a theorem that guarantees this convergence.
Oh yeah, the perceptron convergence theorem.
If the data is linearly separable.
It's a powerful result, for sure.
But what happens if the data isn't perfectly separable?
Oh yeah, that's where the basic perceptron can struggle.
Okay.
It might oscillate between different hyperplanes, never converging to like a satisfactory result.
So what do we do then?
Well, that's where the idea of ensemble methods comes in.
Ensemble methods.
Like calling in reinforcements.
Okay.
Combining multiple classifiers to achieve greater accuracy.
So boosting.pdf talks about that.
Yeah. Boosting.pdf focuses on AdaBoost.
AdaBoost.
It's a popular boosting algorithm.
Okay, so how does AdaBoost create this ensemble of classifier?
It starts with a simple weak classifier.
Okay.
And then it iteratively adds more classifiers to the ensemble, each time focusing on the data points that were misclassified by the previous classifiers.
So it's like correcting its own mistakes.
Exactly. Yeah. It's like each new classifier is trying to fix the errors of its predecessors.
That's really clever.
And the cool part is AdaBoost assigns weights to the different classifiers.
Okay.
So classifiers that perform well on the hard data points get higher weights, giving them more influence in the final prediction.
So like the ones that are doing good get more responsibility.
Exactly. It's like a team leader recognizing expertise. And this weighting scheme is actually guided by something called a convex upper bound on the 0-1 loss.
Okay.
And these upper bounds, like the exponential function mentioned in boosting.pdf, help steer the algorithm in the right direction.
That makes sense.
Boosting.pdf also mentions other ensemble methods like bagging and random forests.
Okay.
Each with its own unique approach to creating and combining classifiers.
Now let's talk about support vector machines, or SVMs.
Okay, SVMs.
SVM.pdf describes them as like finding the dividing line with the widest margin between the classes.
Yeah, it's all about finding the optimal separation.
What does that mean exactly?
Think of it like creating a buffer zone between 2 groups of data points.
Okay.
SVMs aim to find the hyperplane that maximizes this buffer zone.
So like instead of just any hyperplane, it's looking for the one that creates the most space.
Exactly, creating the most breathing room between the classes.
Okay, SVM.pdf mentions that this can be formulated as a convex optimization problem.
Yeah, that's a key insight.
Convex optimization. I feel like I need a refresher on that.
So think of a bowl with a single, well-defined bottom.
Oh.
Convex optimization problems are like that bowl. They have a single, global minimum.
So it's easy to find that optimal solution.
Yeah, exactly.
SVM.pdf even mentions this thing called the Fritz-John optimality condition.
Yeah, that's a bit more mathematical.
Okay.
But it basically helps characterize the solution.
SVM.pdf also talks about slack variables.
Yeah, those are important.
What are those all about?
So slack variables are like safety valves for cases where the data isn't perfectly separable.
Okay.
They allow for a few misclassifications.
So like it's not always black and white.
Yeah, exactly.
So there's some flexibility.
Yeah, exactly.
Now, SVM.pdf also mentions the Pegasus algorithm.
Oh yeah, Pegasus.
What's its role in the SVM world?
It's an efficient algorithm for training SVMs.
Okay.
Think of it as like a finely tuned engine that speeds up the learning process
Okay.
without sacrificing accuracy.
Now, sometimes those linear classifiers just aren't enough. That's where kernels.pdf comes in with the kernel trick.
Ah, the kernel trick.
It sounds like magic.
Yeah, it's a powerful technique.
So can you give me an example of how this kernel trick actually works in practice?
So imagine you have data that can't be separated by a straight line.
Okay.
A kernel function can transform that data into a higher dimensional space
Okay.
where it becomes linearly separable.
So it's like changing our perspective on the data.
Yeah, it's like looking at it through a different lens.
Kernels.pdf gives a bunch of cool examples,
Uh-huh.
like the quadratic kernel.
Yeah, the quadratic kernel lets us learn elliptical decision boundaries
Okay.
instead of just straight lines.
So kernels.pdf also mentions the polynomial and Gaussian kernels.
Yeah.
And the Gaussian kernel is even called universal.
Yeah, it's a very powerful kernel.
What does that even mean?
It means it can approximate any continuous function to arbitrary accuracy.
Okay, so it can basically handle anything.
Yeah, it's very versatile.
Kernels.pdf also points out that kernels can be applied to other algorithms. Oh yeah, like the perceptron.
Like the perceptron.
And ridge regression.
Right.
Making them even more powerful.
So now let's step away from the linear world
Okay.
and talk about decision trees from treepred.pdf.
Yeah, decision trees.
They're like flow charts that guide us to a decision.
Yeah, imagine a series of questions, each answer leading you down a different path,
Okay.
until you reach a leaf node that represents the final classification.
So it's like a game of 20 questions or something.
Exactly. Yeah.
Treepred.pdf highlights the fact that they're very interpretable.
Yeah, that's one of their big advantages.
Okay.
They can be represented as logical formulas.
So we can actually understand why it's making that prediction.
Exactly. You can see the reasoning behind each decision.
Now, treepred.pdf also emphasizes that choosing the right splitting criteria is important.
Oh yeah, for creating the branches of the tree.
So different criteria lead to different partitions of the data.
Exactly.
Okay. And finding those optimal splits is important.
Yeah, it's like choosing the right questions to ask. So if you ask the wrong questions, you get the wrong answers.
Exactly.
Treepred.pdf also mentions that you don't want the tree to be too big.
Right. It can lead to overfitting.
And overfitting is bad.
Yeah, it means the tree is memorizing the training data.
Instead of learning general principles.
Exactly.
Okay, and speaking of things being too big, let's talk about deep learning and neural networks.
Oh yeah, deep learning.
From deep.pdf.
So neural networks are very powerful function approximators. They're inspired by the brain.
Okay.
They have these layers of interconnected nodes.
So it's like a chain of calculations or something?
Yeah, exactly. The output of one node becomes the input of another.
And deep.pdf mentions these things called activation functions.
Yeah, they introduce nonlinearity into the network, allowing them to capture more complex relationships.
So the process of like calculating the output?
Yeah, that's called feed forward, where the information flows through the network.
Now, deep.pdf has this crazy fact.
Oh, yeah.
That a single hidden layer neural network
With enough neurons.
Yeah, with enough neurons can represent any binary classifier.
It's pretty remarkable.
So even like a simple neural network can theoretically learn anything.
Yeah, that's the theory.
But deep.pdf also acknowledges that there are challenges in training them.
Yeah, especially as they get deeper and more complex.
So there's like a gap between the theory and the practice.
Exactly.
Okay, this has been great, but I think we need to take a break and then we'll come back
That's good.
and dive into some more of this stuff.
Okay. Welcome back. Ready to jump back into the world of machine learning.
Definitely. I'm really curious about this idea of consistency that consistency.pdf talks about.
Okay, yeah, consistency basically means that as we feed an algorithm more and more data, its predictions should get closer and closer to the best possible predictions.
So the algorithm's actually learning from the data, not just memorizing it.
Exactly. The risk of making a wrong prediction should decrease as the data size grows, ideally converging towards something called the Bayes risk, which is like the theoretical best performance.
So like a student getting better with every lesson.
Yeah, good analogy. Now, consistency.pdf also mentions these things called non-parametric algorithms, which sound kind of mysterious.
Yeah, what's the deal with those?
Well, think of them like flexible containers. Their complexity grows with the amount of data they're given.
So the model adapts to the data, not the other way around.
Exactly. KNN and decision trees are good examples of non-parametric methods.
Right. But the paper also says that standard KNN isn't always consistent if we keep K fixed.
Ah, good point. You see, if we fix the number of neighbors K, the algorithm's performance might plateau even with more data.
So even with more data, you're limited by that fixed K.
Right. It's like asking the same 5 people for advice even when you have a room full of experts.
Yeah.
But there's a solution.
Oh, what's that?
We can let K grow intelligently with the data size. That way K and N can become consistent.
So it's like expanding your circle of advisors as you gain more knowledge.
Precisely. But this can lead to another challenge, the curse of dimensionality.
Oh, that sounds serious.
It basically means that as the number of features in our data increases, it becomes much harder to find patterns. Imagine looking for a grain of sand on a beach versus searching for it in the entire Sahara Desert.
Oh, wow. Yeah, that's a big difference.
That's the curse of dimensionality. Non-parametric methods can sometimes make this problem even worse because they can become overly complex in high-dimensional spaces.
So do we just give up on high-dimensional data then?
Not at all. We can use parametric methods which have a fixed complexity regardless of the data size. They're more focused and less likely to get lost in the vastness of high-dimensional data.
So it's a trade-off. Parametric models are more targeted. Non-parametric models are more adaptable. Now, surrogate.pdf talks about these surrogate loss functions, which sound pretty interesting.
Yeah, yes. Sometimes the ideal loss function for a problem is just too difficult to work with computationally. It's like trying to climb a steep cliff.
Okay, so surrogate loss functions are like an easier path up the mountain.
Exactly. They're still uphill climbs, but they're more manageable computationally. Surrogate.pdf uses logistic regression as a good example.
Right, logistic regression gives us a probability of something belonging to a class, like whether an email is spam or not.
And it uses the logistic loss function, which is a nice convex function, making optimization much easier.
Okay, so it's like having a map that points you in the right direction, even if it's not perfectly detailed.
That's a great way to put it. Surrogate.pdf also talks about the log odds ratio, which is a way to interpret the output of logistic regression.
Yeah, I was wondering about that.
It basically tells you how much more likely an event is to happen given certain features. Like for spam filtering, it might tell you an email with the word free is 5 times more likely to be spam.
So it helps us understand what's driving the predictions, making things more transparent.
Exactly.
Yeah.
And surrogate.pdf points out that other algorithms like SVMs and AdaBoost also use surrogate loss functions for efficiency.
Cool. Now, deep.pdf had some really interesting stuff about neural networks and their crazy ability to learn.
Oh yeah, the universal approximation theorem is pretty mind-blowing.
Yeah, it says that a simple neural network with enough neurons can theoretically learn any continuous function.
Right, which is pretty amazing, but in practice training, these deep networks can be a real challenge.
So again, there's that gap between theory and practice.
Exactly. Finding efficient training algorithms is a big focus of current research, especially for these powerful, deep networks.
Makes sense. So are there any algorithms that can handle, like, really big data sets or even streaming data?
Ah, great question. That's where online learning comes in.
Online learning, like the algorithm is constantly learning and adapting as new data comes in.
Exactly. Online.pdf focuses on the perceptron algorithm as a prime example of online learning.
Oh, right, the perceptron. I remember that from earlier.
It can process data sequentially, making it super efficient for real-time applications where you have this constant stream of data.
So instead of waiting for a big batch of data, it updates its model with every new piece of information.
Exactly. And online.pdf even shows that the perceptron has bounds on its mistakes, even for data that's not linearly separable.
So it won't go completely off track, even with tricky data.
Right. But what if we have more complex learning tasks beyond simple linear classification?
Yeah, can online learning handle those too?
Absolutely. Online.pdf introduces projected online gradient descent, which is a more general algorithm that can be applied to a wider range of problems and models.
Okay, so how does this projected online gradient descent actually work?
Imagine a ball rolling down a hill, constantly adjusting its path to find the steepest descent.
Okay, I can picture that.
That's essentially how this algorithm works.
Okay.
It updates the model's parameters based on the gradient of the loss function, but it also makes sure the parameters stay within certain boundaries.
So, like, it's following the steepest path down, but staying within the guardrails.
Precisely. And online.pdf shows that this algorithm has good theoretical guarantees in terms of its regret, which is a measure of how much worse it does compared to the best possible solution in hindsight.
So basically, it quantifies the cost of learning on the fly.
Exactly. Online.pdf also mentions strongly convex loss functions, which have a well-defined minimum making optimization even easier for these online algorithms.
So the shape of the loss function matters a lot.
It definitely does. Now, going back to boosting.pdf for a moment, it also talks about this technique called bagging.
Oh yeah, bagging. What was that all about again?
Bagging stands for bootstrap aggregating, and it involves creating multiple copies of the training data by randomly sampling with replacement.
So it's like having multiple students each studying from a slightly different version of the same textbook.
Exactly. Each model trained on these different versions will have a slightly different perspective, and by averaging their predictions, we can reduce the overall variance of the model.
Makes sense. So it's like getting multiple opinions to make sure you're not missing something important.
Precisely. Boosting.pds even shows that bagging can effectively drive the training error down towards zero.
Okay, but we have to remember that bagging is just one of many ensemble methods.
Right. AdaBoost is still the star of the show in boosting.pds, and it goes into more detail about how it works and why it's so effective.
Now that we've covered so many algorithms and techniques, I'm really starting to see how these ideas all fit together.
It's amazing how everything is connected, isn't it? Each piece of the puzzle contributes to our understanding of how machines learn.
Definitely. But I'm sure there's still more to explore. Ready for the final part of our deep dive?
Absolutely. Let's wrap things up and see what other insights we can uncover.
Wow, this deep dive has been a whirlwind tour of machine learning. I feel like we've covered so much ground already.
It's been quite a journey exploring all these different algorithms and techniques.
Definitely. But I'm sure there's still more insights to uncover, right?
Absolutely. One important concept we haven't touched on yet is statistical risk, which statrisk.pdf dives into.
Okay, statistical risk. That sounds a bit intimidating. Can you break it down for me?
Imagine you're trying to evaluate a basketball player. You wouldn't judge their entire performance based on just one game, right?
Right, you'd want to see how they perform over a whole season against different opponents in different situations.
Exactly. Statistical risk is similar. It measures the average loss of a machine learning model over all possible data points, not just the ones we happen to have in our training set.
So it's like taking a broader perspective, considering the model's performance across all possible scenarios.
Precisely. And statrisk.pdf introduces this idea of the Bayes optimal predictor, which represents the theoretical best performance achievable for a given problem. It's like the gold standard we're always striving for, even if we can't always reach it in practice.
So we're aiming for that perfect score, even if it's a bit of a moving target.
Exactly. Statrisk.pdf even shows us how to calculate this Bayes optimal predictor and the corresponding Bayes risk using different loss functions like the 0-1 loss and the square loss.
Okay, so the choice of loss function influences what we consider optimal. Makes sense. Now, how does this theoretical idea of statistical risk connect to the practical concept of test error, which we've talked about before?
Well, test error is what we actually measure when we evaluate a model on a separate data set. It's an empirical estimate of the statistical risk based on a sample of data.
So it's like using a few games to estimate a player's overall season performance.
A good analogy. But as we know, test error can be misleading if the test set isn't truly representative of the real-world data. It's like judging a player based on their performance against just one specific team.
Right, so choosing the right test set is crucial.
Absolutely. And statrisk.pdf even gives some mathematical tools to assess the reliability of our test error. Estimates things like Chernoff-Hifting bounds, which provide probabilistic guarantees.
Okay, so we're not just flying blind, we have some statistical assurances. Now, statrisk.pdf also introduces this bias-variance decomposition, which sounds intriguing. Can you explain that one?
Think of an archer aiming at a target. Bias reflects how far off the archer's average shot is from the bullseye, while variance reflects how scattered those shots are around the average.
So a highly biased archer might consistently miss the target, while a high variance archer might hit all over the place.
Exactly. In machine learning, bias refers to the model's tendency to oversimplify or misrepresent the data, while variance reflects its sensitivity to the specific training data.
And I'm guessing this relates to the overfitting and underfitting problems we talked about earlier.
You got it. High bias usually leads to underfitting the model is too simple and misses important patterns. High variance usually leads to overfitting the model is too complex and starts memorizing the training data.
So finding that sweet spot between bias and variance is key.
It's a delicate balancing act, for sure.
Hmm.
Often reducing one means increasing the other.
Wow, this deep dive has been an amazing journey. We've gone from the basics of supervised learning to exploring the nuances of statistical risk and the bias-variance trade-off. It's incredible how much we've uncovered.
It really highlights the depth and complexity of machine learning. There's so much to learn and explore, and it's constantly evolving.
I'm walking away with a newfound appreciation for both the power and the challenges of this field.
And as we wrap up this deep dive, I encourage everyone to continue exploring, ask questions, challenge assumptions, and never stop learning. The world of machine learning is full of possibilities, and it's up to all of us to shape its future responsibly.
That's a great message to end on. Thanks for joining us on this deep dive into the fascinating world of machine learning.